So hello again. Tonight's another clickbaity type topic, Otter Not So Ridiculous. We're going to be talking about the US Department of Defense DARPA Otter program and why it's not so utterly ridiculous. So what do otters have to do with astronomy? Because it's the name of the DARPA research program is Otter. What they're talking about is very low Earth orbiting, long mission duration craft. If they're hovering over an area, called loitering over an area, then they're not a satellite because they're not orbiting. But if they're that high and they're going around the Earth rather quickly, shorter time period than 90 minutes, then they're satellites. The idea is, how do we fly something very long duration at high enough altitude to make its vantage point worthwhile while still not needing, like heavy rockets to lift it? Because it's not going to be in a long-term orbit, not going to be years to decades, or geo is hundreds of years. It's going to be more like a few months. Which, if you look at a lot of the low Earth orbiting clandestine satellites, they're only up over an area for a few months and then they burn them up. Think about it as it's in space, just not too high in space. So the US government, Department of Defense, has the Defense Advanced Research Project Agency, or DARPA. They have a lot of different programs. They give them all interesting names. What they were looking for is something that didn't require a fixed at launch size fuel tank of combustible fuel. So it could be up there for an extended period of time and not just maintaining its orbit, because satellites can do that for about 5 years, then they run out of their orbital maneuvering or station management fuel. But this thing could stay up there for a year and move around. If it needed to be in a different place, a different orbital angle, a different position, then it could do that without consuming its limited supply of fuel from a tank. So that's the program that DARPA put out, was Otter. I didn't see any acronym for it. It's just called Otter. The idea is to have long duration missions. They're open to development of new propulsion systems. And the program also includes ground test capabilities, so static fire testing inventions and such, plus all of the tools development and support system development necessary for a new kind of craft with a new kind of propulsion. So a lot of new stuff. But I would say, if it's just going to loiter over an area and move to a different area, and it's not actually orbiting, is it still a satellite or just a craft? But there's spacecraft and there's high altitude aircraft, so they're all craft. But the thing that goes around is typically a satellite. They're looking for a mission duration in excess of 1 year. Whenever DARPA does a program, they have what they refer to as a transition partner. So DARPA contracts companies to do the research and development. And once it's kind of a proven thing, then they hand that off or transition it to whatever department of the DoD needs the capability. And if you think about short-lived clandestine satellites that have the ability to move around without much concern of fuel, then that would be the DIA, the Defense Intelligence Agency, the NRO, the National Reconnaissance Office, NSA and CIA, those guys. But I would also think that it could have a use with NASA or NOAA. Let's say it's hurricane season. Hurricane season doesn't last a year, but if a hurricane looks like it's going to form, and you could task one of these things to go over to where the hurricane is forming and keep a close eye on it, closer than an orbiting satellite would, and if it's loitering rather than orbiting, it can just stay on target for up to a year. So every year they could put one of these things up to just monitor the Caribbean. So I think that NOAA would have a strong desire for this for hurricane hunting. So if you want to know where a very low Earth orbit is, or VLEO or VLEO as they call it, it's outlined there in red. You can see it's above the Kármán line, but it's below all the other orbital elevations. So here in the table, you have a mixture between atmospheric bands. That's the troposphere, stratosphere, mesosphere, thermosphere, exosphere. And then you have the demarcation of the Kármán line And then above that, those are all orbiting kinds of things. And the orbiting goes all the way out to where basically you start to attain escape velocities. And there is actually something called the geocorona. So if you're out in space looking back at Earth and you have the right detection equipment, you can actually detect that there are ionized right on the edge of the Earth atmosphere particles. And that's called the geocorona. Like the sun has a corona, strangely enough, the Earth has a corona. But you can see that VLEO is way down low. It's above the Kármán line, but below or low Earth orbit. So what are the benefits of having things at VLEO? Well, you can do clandestine work, Earth resources monitoring, agricultural. If you can loiter over an area of a major metropolitan city, it might be that you could use them for law enforcement. Or if you want to monitor some big public event, you could have them loiter over that area. When you're that much closer, the communications lag from ground to the craft and then back down to the ground is lower. The latency is lower. The time it takes for the signal to get up and down is lower than even Starlink, which is at low Earth orbit. Being that low, you have a narrower field of view. If you think of a geostationary or geosynchronous satellite, it's well up out to the outer edge of the Earth's atmosphere, and it has a hemisphere view. So whether it's looking down with the camera or has a radio antenna pointing down, it can cover like North America with a single craft. If you're a medium Earth orbiting, you can be a GPS satellite, and they're zooming overhead. They take longer than 90 minutes to go around because they're at a higher altitude. And most of the low Earth orbiting stuff like Starlink satellites or the ISS or Hubble Space Telescope, they take about 90 minutes to go around. So the field of view is small enough that you might be able to get an average sized state if you're loitering. I doubt that you could cover all of Texas, California, Florida, or New York. They're too tall in latitude. But a smaller state, you might be able to use one craft that could image anywhere on the entire state, like Massachusetts, New Hampshire, Rhode Island, those kind of things. You may be able to cover a large county, like one craft might be able to do all of Broward County. A large metropolitan city, like you wouldn't be able to do all of Dade County, Broward County, Palm Beach. That'd probably be a bit large, or Los Angeles County. But if you can move without regard to fuel tank exhaustion, then having a county-sized view is good, and being able to move makes it more useful. But what about astronomy? Well, and at the links at the end, I put a link to this. NASA does have a program for pressure-controlled lighter-than-air balloons delivering into the stratosphere, multiple ton class instruments, telescopes, cameras, etc. So NASA's already in the business of, we need to get this just a little higher and last a little longer. The lighter than air balloons, where they control the pressure of the helium inside of them, they last just less than a year. And if this thing can stay up longer than a year, NASA might be interested in that. Whatever the tonnage is of their payload. Now, if they're clandestine observing instruments, they're probably going to be able to take a ton or more up. And so that falls into the same category as the kinds of observing instruments that NASA's launching from balloons. So you could use it for looking down for environmental resources monitoring, looking up out into space. If you remember the 747 Sophia, think of this as an uncrewed variation of Sophia, but Sophia could only get to the stratosphere, about 45,000 or so feet. This can go up several times that altitude. So if you could get something with the instrumentation of a Sophia, which was infrared, and you could put it up and have it last for a year, hovering over a specific area, then you could get some long duration monitoring without having to worry about flying home every night. And there's no crew on board, so it's a lot less expensive than Sophia would have been. Now, if you want to recover your instruments with the balloons, they actually include parachutes, so that when the mission is over, they cut the balloon loose and they use the parachutes to recover the very expensive telescope. It obviously has enough parachute that it doesn't damage it when it hits the ground. And then they can retrofit it with new instruments and reuse it for future missions. So this would be the same sort of thing. The only difference would be that these craft would need to be somewhat aerodynamic, and we'll get into why that is. So there's a company called Redwire Space. They are a go-to contractor for the US military and for NASA for various technological aspects of things in space. So they've worked on pressure systems and valve systems and electronic controls, and they're really a go-to kind of company. And so DARPA Otter program has let a prime contract out to Redwire Space to develop what is known as the Sabre Sat. Sabre because isn't it cool? It's a name, Sabre. And when I show you kind of what it looks like, you'll realize if you remember the F-86 Sabre aircraft, if you take off the wings off the side, this thing kind of looks like a Sabre aircraft. So that's why it's called Sabre. And it's a satellite, so Sabre Sat. But Redwire Space is also working with the European Space Agency. DARPA has its Otter program. The ESA has its Phantom program. Its SkimSat program. And that aircraft is called Phantom. Talk about clandestine out in the obvious. But there are apparently multiple countries interested in very low Earth orbiting for a variety of purposes. Redwire Space refers to these craft as orbital drones. To me, that says, obviously, no crew on board, but also, obviously, if it's a drone, that means it flies autonomously. You get it up there and you task it with missions. It goes and does a mission, and then you tell it where to go back and loiter again, or what orbit to attain. So it's likely to do what it needs to do on a mission tasking, and then come back to wherever you want it. So it has the ability to reposition itself using the air ionization engines. Apparently, the only fuel they need is electricity from solar cells. So there's nothing burning. There's no fuels being dumped over catalytic converters. So it'll be interesting to see how they maneuver with it. Now, because it's a DoD proprietary program, I can't show you the actual pictures, but I have a little diagram down there at the bottom. It has an elliptical long tube body. And if you look at it from the front, it has that elliptical opening like a F-86 Sabre jet aircraft would. And then it narrows down towards the back and comes out elliptical at the back and has two of these ionization engines out the back. It has two tail fins. I don't know what they use those for since there's not quite enough air to do things, but you have to be somewhat aerodynamic in that there's a few air molecules left up there. That's actually what they're consuming in order to do their propulsion. And on top, sort of like a fin off the top of a shark or a whale, is the solar panel. So the solar panel has to be double-sided because you can't tilt it or twist it. It's just going to be whatever direction it's flying. It has to pick up the sun from whichever side it can get it on. And that's how it gets its electricity. But it scoops in low-density air molecules in the front, compresses them, and then uses the electricity to ionize the oxygen and nitrogen in the atmosphere to use as propulsion. Think of it as air-burning ion propulsion. And if you know ion propulsion, it's not a lot of massive thrust. So if you want to move it somewhere using this sort of propulsion, it'll take you a little while. Maybe hours, maybe days, but no fuel tank. So what do you do with one of these things when it's done? If you use a rocket to launch it, it's obviously not going to have enough fuel to make its way back down successfully and be recoverable. But if you design it with some fixed fuel supply just for reaction control system thrusters, then it could use that to deorbit itself gracefully and maybe have a parachute on board. So you wouldn't have to build a new one of these things every time you wanted one up there. You could retrofit it, clean it up, reuse it. If it's not recoverable because no RCS and no fuels for doing that, then it'll likely burn up in the atmosphere. But you have to design it so that all the parts burn up. From the earlier spacecraft that mankind has put up into orbit, we've realized that tanks, like fuel tanks, oxygen, hydrogen, helium, all those big, heavy pressure fuel tanks with critically low temperature fuels, they're hard metal. They don't burn up so easily. And bulkheads, if you've got dividers down the length of your spacecraft, or the outer cylindrical has bulkheads in it, those bulkheads are very high strength metals, and they don't burn up as well either. There are UN guidelines now for designing your spacecraft so that when they re-enter, that they more fully burn up. So they're taking that into account. I would also think that technical malfunctions are just something that can happen. Or if you're doing clandestine work, like, U2 did once, you can be shot down by an adversary by a missile. So that would early end your mission, and your reentry may not be controllable, or as I like to refer to it as, if it happens, duck and cover. So if that's the case, and they want to do this often, expect governments to establish avoidance clauses for liability for damage or personal injury from falling LEO debris, particularly if it's debris that falls in a clandestine fashion somewhere you didn't know it was there, if it was just loitering. So what are the downsides to these air-burning VLEO craft? Well, it's ionizing what little air is there, which means it energizes the air molecules, heats them up, accelerates them, ionizes them. And in the process, it consumes oxygen and nitrogen through chemical recombination, high temperature recombination. It emits ozone and nitrous oxide. So if only a few of these craft are doing this, probably not a big deal. But if somebody said, I want to put up a constellation of Otter satellites, now you've got a lot more ozone and nitrous oxide being spewed just above the stratosphere. I don't know what the downside of that is that you have to mitigate, but I would think it would be of concern. The other thing to think about is that the Earth's atmosphere is not perfectly spherical. It's not like a ball with fixed layers. Depending upon the density of the ground below a particular area, whether it's mountainous or not, and whether the sun is currently beating on it or not, you can have different densities of atmosphere. So when this particular craft is flying through an area with higher density, it needs to scoop up more air molecules and compress them into a tank so that when it's flying over an area where the air density is lower and it has to do maneuvering, it has the air available for ionization for doing whatever it wants to do with its thrust. So the front end has to be able to suck in, like a jet airplane's aperture can suck in air, and then the exhaust comes out the back, and the usual Newtonian F equals ma kind of thing happens. So when the tank is full and it can't take any more air in for compression, and at the moment the engine's not running because it's just free coasting its orbit, then the intake scoop that's now sealed off becomes a drag source. And the other thing they found out was, because even low density air has oxygen in it, and you're operating at multiple times the speed of sound in your orbit, that oxygen will find its way to oxidize or corrode metals. So the oxygen on its way in becomes its own friction source and ablates the scoop metal, the compressor metal, the pumps and tanks metals, because these molecules may be low density, but they're traveling potentially in the opposite direction to where you're traveling at multiple times the speed of sound. So heavy impacting molecules. So they need to have this tank on board, because if they want their mission duration to be up to a year, they have to come up with a balance of when they can burn the engines, when they can't, when they have to suck in more air, when they can't. So that'll go into the autonomous design of it, for it to figure out when it needs to fill up its tank. And depending upon whether they're loitering or orbiting, the actual reentry will need to be taken into account. And they also need to consider unplanned malfunctions or shoot downs and the reentry associated with that, either as a whole mass or lots of pieces. As usual, I have an alternative for fuel-based propulsion. So even if it's air burning with the low pressure air that gets compressed in, it's still chemical propulsion. It's ionization of the available air, and that corrodes components. And there's also the issue of nitrous oxide emissions, even if you ignore the ozone emissions, saying, well, adding ozone to the atmosphere is a good thing, isn't it? At certain elevations, yes, but nitrous oxide is not. So my approach is skip the whole concept of ionization and burning. Use radiation reflection pressure. You can continue to use solar power and batteries for your fuel source. You know, if you had, instead of rocket engine nozzles out the back, you had up front, you had reflectors, conical reflectors. They were taking in photons and using the transfer of momentum to propel the craft forward. The thrust would still be on par with like ion engine level. It wouldn't be massive. It's not an F equals ma because there's nothing coming out the back, which makes it more clandestine. You know, there's no atmospheric density issue. There's nothing that there's no RCS thrusters. There's no gyroscopes. There's no aerodynamic control surfaces. It gets rid of all that stuff. There's no fuel tanks, plumbing, valves, combustion chambers, makes the craft lighter. No corrosion from oxygen because you don't have an intake. There's no exhaust pollutants that could clog up your sensors. Craft is lighter, smaller. Mission duration might actually be upwards of 5 years, which is kind of the continuous output lifespan of these high output LEDs, about 5 years. So go from 1 year to 5 years. So my take on very low Earth orbit is, you know, whether they're using compressed air burning or not, extended mission craft, whether you're orbiting or loitering, it's going to be developed. There's just it's too great an opportunity to be passed up. Too much benefit for the U.S., its military, its allies, and its adversaries. So, you know, we're doing it. NASA, not NASA, but DARPA, European Space Agency's doing it. I've got to believe that other nations are doing it as well. Some of them are our adversaries. So what's the phrase? We must not have a mine shaft gap. Movie buff, I can't help it. But some technological issues need to be solved. And that's why DARPA is contracting this out to Redwire Space to find out all the edge conditions and then find ways to mitigate it. I think that air burning, even if it's ionization, is still kind of clinging on to the past ways we've done things. And I think it's well past due to move on to something that has less fixed fuel tank, as they refer to it, regret.
I have a question.
Yes.
Okay, yeah, maybe it'll come up in the conclusion, so maybe I should wait.
That's okay.
But I was looking at that screen, the VLE, the alternative, and I'm wondering, now is that in are they utilizing the alternative now? And what is the downsides of using the alternative? I heard the upside, but I might have missed the downside.
I have an entire presentation on the YouTube channel on photonic propulsion and EM drive.
Right, yes.
Yeah, and it has the pluses and minuses in there, but the pluses are, you know, simpler, smaller, longer duration craft, cheaper to build. The downsides are it's, for want of a better way of describing it, where ion propulsion was 40 years ago when it wasn't taken seriously. Now that it's taken seriously, nobody doubts it. Well, it's the same sort of thing. Until ion propulsion started to gain some respect and funding, there was no proof of it. There was a spacecraft called Deep Space One that was the first deep space craft that used ion propulsion. And as the saying goes, it went off without a hitch. And then afterwards, now there's lots of different craft, Earth orbiting as well as deep space, that all use ion propulsion because it was proven out. If radiation reflection pressure is a thing in physics, which it is, there's a Nobel Prize for a guy that used it to develop tweezers based upon photons pushing things, spend some money on it, prove it out. And I think you'll find that it's a lot better than any fuel combustion based propulsion we have today for those missions where you don't need, massive launch thrust at liftoff. But for
So you're
orbital,
saying they are using it today. They are using it today, but not in as many things as they could.
no, for ion propulsion, they definitely are. I'm talking about photonic propulsion. There's a lot of edge testing, but there's no serious programs for it. Unless it's clandestine, DARPA hasn't publicly identified any contract money for it. Neither has NASA. But occasionally they do, like the NASA Eagle project, where they evaluated the EM drive. EM drive is not optimal. It may be photonic propulsion, but it's nowhere near as optimal as can be practically done with existing technology. So, yeah, I think that NASA needs to take another look at it, not spend billions on it, not even hundreds of millions, probably just a small single-digit number of millions to get a team together, get a program, have access to the materials fabrication and the NASA testing facilities. And I think they'll find that it's on par with ion propulsion. The benefit is ion propulsion runs out of gas. And if you don't think so, we've had, deep spacecraft that have moved from asteroid to asteroid or comet to comet, and eventually they wind up either crashing into or going into a long duration orbit around the last thing that they got to because they ran out of their xenon fixed supply of gas for thrusting. And even the SpaceX satellites, they found it cheaper to use krypton gas instead of xenon. And they have a lifespan of 5 years. And it's not because the electronics die after 5 years. It's because they run out of gas, krypton. So I think it's something that definitely needs to be investigated. Okay, in conclusion, it may be spelled the same, pronounced the same, but there's an animal called an otter, and there's the DARPA Otter program. Very low Earth orbiting things have a unique advantage over the higher ones. Up to this point, VLEO has been basically inaccessible because if you use a normal burning fuel to make a rocket orbit, because there's atmosphere left at VLEO where there isn't atmosphere or less atmosphere at LEO, you're going to burn up your fuel too quickly. So you have to have an alternative propulsion source. Combining solar power, air compression, and ionization, it still has its limits, but it's kind of like the next baby step to allowing craft to be developed for VLEO. And DARPA has contracted Redwire Space to develop and test their SabreSat demonstration craft. Maybe DARPA should also contract for development and testing of radiation reflection pressure, but that's just my humble opinion. And then we have links to all sorts of things. And if you want to know about Redwire Space and those very large balloons that NASA launches from the Antarctic. And then if you want to know about radiation reflection pressure, there's a YouTube video I put out. Okay. Comments, questions, curiosity? Had anybody heard of VLEO previously?
Nope.
Well, that's good then. People learning new things.
Learn something new.
Yeah. Think of 5 impossible things before breakfast. Alice in Wonderland. Okay. Any comments or questions before I stop recording?
No.
Hearing nothing.